How do you just look at 321 and know that it represents the number 321? And why does it have to be this way? Why can't it represent, say, 86? Whether you're conscious of it or not, you've been trained to think in terms of tens. Let's think of this number in terms of USA cents. Then the ones column on the right is our pennies column, since we have 1 cent in a penny. Since we have a 1 digit in this column, we'll have 1 penny. The next column over will represent 10 pennies, so it'll be our dimes column. And the 2 in this column tells us that we have 2 dimes. Finally, the column to the left of that will represent 10 dimes, so it'll be our dollars column. Because we have a 3 in this column, this then means that we have $3. So we have $3, 2 dimes, and 1 penny for a total of 321 cents. If we add a column on the left, then it'll represent 10 of our dollars column, so it'll be our $10 column. The 4 in this column would then add an extra 4 of our former $10 Eagle coins. This would add 4,000 more cents to make a total of 4,321 cents. But now, what if the columns meant something different? What if instead of 10, we used 5? Well, we'd still have 1 penny, but now the 2 would represent the number of nickels we have, because there are 5 pennies in a nickel. The 3 would now also represent something different. It would represent the number of quarters we had, because there are 5 nickels in a quarter. Under this interpretation, 321 would mean we had a total of 3 quarters, 2 nickels, and 1 penny for a total of 86 cents. And if we worked with fives, we wouldn't need to use the digits 5, 6, 7, 8, or 9. If we had 5 pennies, we could use a nickel instead. And if we had 5 nickels, we could use a quarter instead. So maybe we'd be better off if we worked with fives. But now what if we worked with twos? So what if each column represented 2 of its neighboring one on the right? As an example, let's look at the number 1010 in terms of cents. The column all the way on the right tells us we have no pennies. The one to the left of it would then tell us that we have 1 old US coin that no longer exists, the 2-cent piece. The one to the left of that column would represent 2 2-cent pieces, some made up 4-cent coin. But this column is a 0, so we have no such coins. Finally, the column all the way on the left would represent 2 4-cent coins, or some made up 8-cent coin. And we have 1 of these. So in total, we have 1 8-cent coin and 1 2-cent piece for a total of 10 cents. Therefore, in this light, 1010 would coincidentally represent the number 10. What's great about this system is that we only need zeros and ones. If we ever had 2 pennies, we could use a 2-cent piece instead. If we ever had 2 2-cent pieces, we could use a 4-cent coin. And if we had 2 4-cent coins, we could use 1 8-cent coin. This is the so-called binary system of computers. Ever see all those zeros and ones in one of those Matrix movies? Well, that's how our computers view the world, and those are the only digits they need. In Crazy Coins, you will be exposed to a bunch of new coin amounts, and you'll be asked to translate our system of tens to a system of fives or twos or some other number. Let's say, for example, that you're given the amount 86 cents, and you're working in the realm of fives as before. So the column on the right is the 1 cent or pennies column. The neighboring column to the left of that one is the 5 cent or nickels column. And the neighboring column to the left of the nickels one is the 5 nickels column, or the 25-cent quarters column. Then you have to figure out that 86 cents is 3 quarters, 2 nickels, and 1 penny. So you'd select 3 under 25 cents, 2 under 5 cents, and 1 under 1 cent. Almost instantaneously after you have a correct answer, which in this case would be when you select that final 1 under 1 cent, the columns will all deselect and you will hear a sound that resembles a piece of silverware hitting a glass. You will then be presented with a new question. In this case, the new amount is 65. Try to answer as many questions as you can in 60 seconds. We hope you enjoy this game, which will sharpen your basic math skills and hopefully make you realize that there really is nothing special about the number 10. And 321 doesn't need to represent 321.